Piping vibration, specialist measurement techniques, advanced tools and methods for precise data collection. This presentation refers to guidelines for the avoidance of vibration-induced fatigue failure in process pipework by Energy Institute. Introduction to specialist measurement techniques. Specialist measurement techniques are advanced methods used to obtain detailed information beyond basic vibration measurements. These techniques are essential for diagnosing complex issues in mechanical systems, particularly in piping and structural components. They provide insights into fatigue risks, dynamic behaviors, and operational conditions that standard vibration analysis cannot reveal. The primary techniques include dynamic strain measurement, experimental modal analysis, operating deflection shape, ODS, analysis, dynamic pressure, pulsation, measurement, and transient vibration measurement. Each method serves a unique purpose. Dynamic strain measurement evaluates fatigue potential by measuring strain near critical weld points. Modal analysis identifies natural frequencies, damping, and mode shapes. ODS analysis visualizes the dynamic motion of systems under operating conditions. Pulsation measurement quantifies pressure fluctuations in fluid systems, and transient vibration measurement captures short-lived events through continuous data recording. These techniques collectively enhance reliability, safety, and performance by enabling engineers to predict failures, validate designs, and implement corrective actions promptly. Understanding their principles, applications, and limitations is crucial for effective maintenance and troubleshooting in industries such as energy, manufacturing, and transportation. Purpose and methodology, fatigue assessment and SN curves. Dynamic strain measurement is a critical technique for assessing fatigue failure risks in structural components. Unlike basic vibration analysis, which only provides preliminary screening, dynamic strain measurement offers direct insight into whether fatigue will occur. The process involves placing a small uniaxial strain gauge near the weld toe, typically within 15 mm, with a gauge length under 10 mm. Several attachment methods exist. Bonded gauges require surface preparation and are time-consuming. Weldable gauges are suitable for high-temperature environments, and press-on gauges offer rapid deployment for operational assessments. The strain data collected can be converted into stress values using Young's modulus. Assuming uniaxial conditions, which is reasonable for most fatigue modes involving bending. These stress ranges are then compared against fatigue design curves, such as those in BS 7608 or PD 5500, which provide endurance limits based on weld geometry. If measured stress exceeds the endurance limit, for example 35 MPa for Class F2 welds, immediate corrective action is necessary. Even readings above half the limit warrant remedial measures to prevent long-term damage. This technique is indispensable for ensuring structural integrity and preventing catastrophic failures in critical systems. Fatigue assessment using dynamic strain measurement relies on SN curves, which plot stress range against the number of cycles to failure. Standards like BS 7608 and PD 5500 provide these curves for various weld classes, derived from extensive testing of specimens fatigued to failure. The design curve typically represents the mean minus 2 standard deviations, ensuring conservative estimates for safety. The endurance limit, often set at 10 to the power of 7 cycles, indicates the stress level below which infinite life is assumed. For example, in weld class F2, a dynamic stress range exceeding 35 MPa peak-to-peak requires immediate action, while values above 17.5 MPa suggest remedial measures. These thresholds help engineers prioritize maintenance and prevent fatigue-related failures. By integrating strain measurements with fatigue curves, engineers can accurately predict component life, optimize inspection intervals, and implement design improvements. This approach is vital for high-stress environments such as power plants, offshore platforms, and heavy machinery, where fatigue can lead to costly downtime or hazardous incidents. Principles and applications, experimental modal analysis. Experimental modal analysis is a technique used to determine the dynamic characteristics of structures, such as natural frequencies, damping ratios, and mode shapes. The process involves exciting the structure with a known input force, typically using an electrodynamic shaker or an impact hammer, and measuring the resulting vibration response. The ratio of vibration response to input force across frequencies forms the frequency response function, FRF, which provides critical insights into the system's behavior. Modal analysis is invaluable for validating finite element models, identifying resonance issues, and improving design robustness. Accurate data collection requires minimizing background vibrations during testing to avoid interference. When measurements are taken at multiple locations, mode shapes can be visualized, aiding in understanding how the structure deforms under dynamic loads. This technique is widely applied in industries such as aerospace, automotive, and energy, where structural integrity under dynamic conditions is paramount. By identifying problematic frequencies and damping characteristics, engineers can implement design modifications or damping solutions to mitigate vibration-related failures. Characterizing dynamic motion, operating deflection shape analysis. Operating deflection shape, ODS, analysis is a powerful tool for visualizing the dynamic motion of a system under actual operating conditions. Unlike modal analysis, which uses controlled excitation, ODS relies on simultaneous vibration measurements at multiple points during steady-state operation. These measurements provide amplitude and phase information relative to a fixed reference, enabling engineers to construct a clear picture of how the system moves at specific frequencies. ODS analysis helps identify problematic areas, such as excessive displacement or unexpected motion patterns, which could lead to fatigue or failure. It is particularly useful for troubleshooting complex piping systems and machinery where theoretical models may not fully capture real-world behavior. By understanding the operating deflection shapes, engineers can implement targeted corrective actions, such as adding supports, modifying layouts, or adjusting operating parameters. This technique enhances reliability and performance by ensuring that dynamic motions remain within acceptable limits. Measurement techniques and challenges. Dynamic pressure measurement, or pulsation analysis, is essential for evaluating pressure fluctuations in fluid systems, such as those involving compressors and pumps. Standard static pressure transducers lack the response speed needed for accurate pulsation measurements, especially at higher frequencies. Instead, dynamic pressure transducers based on strain gauge or piezoelectric technology are used, offering wide frequency bandwidth capabilities. A key challenge is introducing the transducer into the fluid stream without creating measurement errors. Long tappings can cause acoustic resonances in the resulting dead leg, distorting readings. To mitigate this, measurements should be taken at multiple locations along the same line, reducing the risk of capturing data at pressure nodes where amplitudes are minimal. Despite these precautions, limited measurement points may still fail to represent maximum pulsation levels due to standing wave patterns in the fluid. Industry standards provide pulsation criteria for specific applications, but engineers must interpret results carefully to ensure accurate assessments. Effective pulsation measurement helps prevent issues such as vibration-induced fatigue, noise, and system inefficiencies. Capturing and analyzing transients, measurement of transient vibration. Transient vibration measurement focuses on capturing short-duration events that can significantly impact system integrity. These events may occur during startup, shutdown, or unexpected operational changes. Continuous data recording is essential for capturing transient time histories, as these events are unpredictable and brief. Modern digital recording systems enable high-resolution data collection across multiple channels, allowing comprehensive analysis in both time and frequency domains. Engineers can identify transient peaks, correlate them with operational conditions, and assess their potential to cause damage. This information is critical for improving system design, implementing protective measures, and optimizing operational procedures. By understanding transient behaviors, industries can prevent failures, reduce downtime, and enhance safety. The ability to analyze large volumes of transient data also supports predictive maintenance strategies, ensuring that corrective actions are taken before issues escalate.